Right, so first of all, some very basic understanding. These are very basic things. It's so basic that I guess even a primary school student can understand. Right, so what we have here is something about tension and compression. Right, so what you have on the first figure is you have a member. Right? It doesn't matter what material, timber, glass, plastic, concrete, steel, whatever. If you have a member and you try to apply the loading like this, you try to pull the member. So what you have is you try to apply a loading like this. Right? If you try to pull it like this, so the member is under tension. So to light it. Right, so what happened to this member is if you try to apply a loading like this, you try to pull it like this, then of course the member will get longer, right? So it will get longer. In the direction of the loading. Right, so this piece of material will get longer in the direction of the loading T. So I better put it down in the direction of your tension T. The technical term for gets longer is elongation. Right, that's the technical term. That's a noun. The verb is elongate. Elongate. Right, so that's simple enough to understand. Right, so if you have a material and if you apply a loading or a force T along this direction, so that piece of material will get longer along that particular direction. Right, so, but what I try to emphasize is, if you, I can describe the same thing, like, if this piece of material gets longer in this direction, that implies there must be a tension force in the same direction. Okay? So I'm saying the same thing, but in the reverse direction. If you have, so first, if you apply tension like this, there will be elongation along that direction. But if I repeat the same sentence, but in the opposite direction, then you say, if this piece of material gets longer in this direction, then it implies there is tension along this direction. Okay? So, elongation and tension is just sort of a couple. Right? If you have tension, you have elongation. If you see elongation, that implies there must be tension. Okay? So that's what I mean here. And then the same thing, if you have the same piece of material and you try to compress it this time, instead of T, you try to compress it. Right? You apply your loading like that. Right? You compress it. Then what happens? So obviously, this thing will get shorter, right? Just like this piece of material. If you compress it, what happens? It will just get shorter. Right? So if you compress it, then it gets, instead of longer, it gets shorter. In the direction of your compression C. And the technical term is shortening, or the verb is shortened. So just like elongation and tension, I can also write shortening implies compression. In other words, if you see a piece of material that gets shorter along this direction, then that implies there must be compressive force along that direction. Right? So in reinforced concrete, everybody knows there are two elements, concrete and steel reinforcement, right? So concrete is usually responsible for taking up the compression. So concrete in a reinforced concrete structure, right? Concrete is supposed to take the compression part, the compressive load. So why it takes compressive load? Because that is something you learn in your material part. Concrete is weak in tension. It's very weak in tension actually. So if you got a piece of concrete, you try to pull it, what happens? It cracks. And it breaks into two parts, or many parts, easily. Right? Because concrete is very weak in tension. It's relatively strong in compression. So that's why in reinforced concrete structures, concrete is responsible for carrying compression. Carrying compression. Okay, so for steel reinforcement, everybody knows that steel reinforcement in a RC structure is responsible for taking tension or compression, both. Right? But primarily it's supposed to take tension. So steel reinforcement, in short, we call it steel bars. So steel bars, steel is strong in both compression or tension, but in RC structure, it's supposed to carry tension. And this is the reason why you put these two materials together in a reinforced concrete structure. So those simple things you should have learned it before in your contact or material course. Right, so before we look at bending, we also need to do a quick revision. Something you should also have learned in your material part. So what is it? So the thing that we need to know in a reinforced concrete structure, those two materials, is how much compression can a piece of concrete take. So suppose you have a piece of concrete like that and you try to compress it. And you try to find out how much load, how much compressive load, how much C that this piece of concrete can take. So you do an experiment, or experimental base. So you put it in a machine and you try to compress it until it breaks, it crushes. The technical term is it crushes. Until it crushes. So if you do such an experiment, you would find something like this. Right, so on the vertical axis, that is your C. So you keep increasing your compressive force C. And on the horizontal axis, you know what to measure. When you compress something, it shortens. So you try to measure the shortening. Of course, the magnitude of shortening is actually very small. so small that you could not see it, you can only measure it. Okay. 究竟壓短咗幾多你係肉眼睇唔到。Okay. You can only measure it through your instrument, but you can't see it. Right, so if you do this experiment, what happens is, if you plot C against shortening, it's not a straight line, it's sort of a parabolic until Thomasine. So it would something like this, until it crush after surgery, or you can call it, technical term is compressive failure. So obviously this is not a straight line. It's a sort of parabola. Thomasine. Okay, so that's what happens if you try to compress a piece of concrete. What about if you try to pull a piece of concrete? As we said, concrete is very weak in tension. If you try to pull a piece of concrete, that's something you can easily imagine. Right? So this is concrete. This is also concrete. But instead of compressing it, you try to pull lightly. Right? Then what happens? You won't be able to trace such a graph because it's so weak. Once you try to pull, it cracks. Lead hole. So it cracks. Don't mix up these two words. Crush is only when concrete under compression. Crack is the word you use when the concrete is in tension. So don't mix up these two words. Completely different. So when you try to pull a piece of concrete, it cracks. So how does it crack? So you can draw some crack line like that. So what that means is, if you try to pull it in this direction, then the crack will form in this direction. And by just looking at these two directions, you can tell they are perpendicular to each other. Right? This is the direction you try to pull, and that's the direction of the crack lines. So it's sort of perpendicular to each other. And you don't need to apply much load, just a very little T. It's able to crack this piece of concrete because concrete is very weak in tension. But if this is a piece of steel, then the story is different. Right? If this is a steel ball, a steel reinforcement, if you try to pull it, and the objective is you try to find out how much load this steel bar can carry or can take. So you keep pulling until it breaks into two parts, it fractures. So you can do such an experiment, and from the experiment you can trace the graph. Of course, this time you plot tension against not shortening, elongation. Right, you try to trace how this bar gets longer, by how much when T reaches a certain level, right? So what happened in the experiment, initially it would be a very steep straight line. 開頭係條好斜嘅直線. Right? So it's sort of like this. 一條好斜嘅直線. Right? Like that. Until this T reaches a certain value, right? Until T reaches a certain value. Of course, you can see that when you keep applying T, the things gets longer. That's why you call it meditation, right? But when T reaches a certain value, this line suddenly change from a steep line to a horizontal line. Like that. So this part is called yielding. You should have seen this in your material part. And it yields for a certain distance, a pretty long distance, and then it climbs up again until the very last minute it fractures. That means it breaks into two parts. The most important, if somebody asks you what's the major difference between concrete and steel, first, concrete is weak in tension. That's probably the most important number one difference. The second, number two difference between concrete and steel is, if you just look at these two graphs. In steel, there is a very long yielding region, this horizontal part. In concrete, you will never see this thing in concrete. Okay, what does this yielding actually mean? I suppose you have seen this in your material part. What does the horizontal line in the graph mean? So you can see in the graph a bit over easy. It means that T in this region, T is constant. Right? T is constant in this region. But the elongation keeps increasing. So this part, what yielding means, it's T is constant, but the elongation keeps increasing. So what happened to that reinforcement is, initially, if you try to pull, 你不斷加力咧，佢就越伸越長。去到呢個位，你唔需要再加力上去。呢條鋼筋當然唔係橡筋，呢條鋼筋就會自動不斷伸延。Just gets longer and longer and longer without increasing T, right? That's what happened in the material in this region. You don't need to increase T. It will just get longer and longer and longer by itself. 佢只會不斷增長。Okay, that is the yielding part of a steel bar. That's the second major difference from concrete. And then it yields for a certain distance, and then it climbs up again. So you need to increase T again. And then finally it breaks into two parts. Okay. So here I